Welcome to the third and final PV1X recap video. In the first two PV1X recap videos we covered all the electrical losses that occur in solar cells. In this video we will take a look at the optical losses. First and foremost are the spectral mismatch losses. But to understand spectral mismatch we first need to understand light. Light consists of electromagnetic waves. Visible light with a wavelength of about 400 up to 700 nanometers is only a very small part of the electromagnetic spectrum. Our sun only emits light in the ultraviolet, visible and infrared part of the spectrum. The spectral emission takes the shape of a black body emitter as described by Planck's law. The spectral irradiance on Earth differs from the spectral irradiance in space due to absorption in the atmosphere. For the solar spectrum on Earth we often use the air mass 1.5 spectrum, which has a total intensity of about 1000 watts per square meters. The AM 1.5 indicates that for this particular spectrum the path length of light through the atmosphere is 1.5 times the path length under normal incidence. Consequently, the AM1 spectrum corresponds to when the sun is right overhead, and AM0 corresponds to the spectrum in space near Earth for when light has not traversed through the atmospheres yet. In PV1X you have learned how to relate different properties of light. If, for instance, we start with the AM 1.5 spectral photon flux, here indicated by the black curve, we can obtain the spectral power density here in blue from the spectral photon flux by multiplying the number of photons of a certain wavelength by the energy of a photon here in red. With Planck's constant and the speed of light we can calculate the photon energy from its wavelength. We can obtain the irradiance here in green from the spectral power density by integrating over the full wavelength range. With the solar spectrum in mind we can understand the spectral mismatch losses. Semiconductors have a certain bandgap energy and photons have a certain photon energy. If the photon energy is smaller than the bandgap energy, they will simply pass through the semiconductor material. The semiconductor material is essentially transparent to these photons. If a photon with an energy greater than the bandgap energy is absorbed, a valence electron will be excited high into the conduction band. Shortly after excitation, this electron will relax back to the conduction band edge. The excess energy is thereby converted into thermal energy, which is lost. From these two effects, non-absorption and thermalization, we can see that there is a trade-off when selecting the bandgap of a solar cell. A large bandgap means high non-absorption losses, while a low bandgap means high thermalization losses. Silicon, for instance, with its 1.1 electron volt bandgap can only use the pink fraction in this image. But a solar cell has more optical losses besides the fundamental spectral mismatch losses. The additional losses can be grouped into four categories. Here we see a schematic drawing of a crystalline silicon solar cell. Solar cell exhibit losses due to shading by the front contacts, reflection of the front surface, parasitic absorption in the supporting layers in a solar cell that are not photoactive, and finally transmission losses. Reducing these losses requires understanding of what occurs inside and at the interface of two different media. The absorption inside a medium is described by the Lambert-Beers law, which describes the exponential decay of light intensity as it propagates as a function of the absorption coefficients of the absorbing medium. At an interface between two media, a fraction of light is reflected and a fraction is transmitted under a refracted angle. The angle of refraction depends on the refractive index of the material, which is wavelength dependent. This means that a beam of white light can be broken up into its colorful constituents. Snell's law describes how light is refracted and reflected, depending on the refractive indices of the media involved and the angle of incidence. If the angle of incidence is greater than a certain critical angle, total reflection will occur. This only occurs when light moves towards a material with a lower refractive index. Snell's window is an example of total internal reflection. Total internal reflection has important implications in photovoltaics, as materials and geometries can be chosen such that the absorbed intensity in a device is maximized. Where the angles of refraction are described by Snell's law, the reflected and transmitted intensity are described by the Fresnel equations. These equations distinguish between S and P polarized light. S polarized light has a perpendicular electric field with respect to the incident plane, where P polarized light has a parallel electric field with respect to the plane of incidence. The reflected and transmitted intensities can be calculated for S and P polarized light with the Fresnel equations. For normal incidence, the reflectivity and transmissivity are the same for both polarizations, and therefore the equations simplify. Natural light sources emit unpolarized light, which contains equal amount of S and P polarized light. We showed that the difference in reflectivity between polarization is greatest at the Brewster angle. Snell's law and the Fresnel equations hold as long as the interface is of macroscopic scale. Light starts to behave differently if it interacts with microscopic particles. For particle sizes smaller than the photon wavelength, Rayleigh scattering occurs, which causes light to be effectively scattered in all directions. Moreover, Rayleigh-sized particles are very effective at scattering small wavelength photons, which is why the sky appears blue. When the particles and the photon wavelengths are of roughly equal size, Mie scattering occurs, which is less wavelength dependent and therefore scatters all visible wavelengths more or less equally. Mie scattering occurs predominantly in the forward direction, which explains why a setting and rising sun appears red. Rayleigh and Mie scattering have to do with the principle of diffraction. Diffraction is the bending of light around an obstacle. If multiple diffracted waves superimpose, interference occurs. We derive the amplitude for a superimposed wave. A phase shift of 0 or multiple of 2 pi between two superimposed waves leads to constructive interference. A phase shift of an uneven number of pi's leads to destructive interference. In PV1X, we showed that interference effects can be used in solar cells in a number of ways. For a certain spectral range, destructive interference can be used to create an anti-reflection layer at the front of the solar cell. On the other hand, constructive interference can be used to create a dielectric back reflector to maximize reflection in a certain spectral range at the back of the solar cell. Finally, we discussed how diffraction gradients can be designed to diffract the light into wide angles. This effectively increases the path length of light through the cell. Having discussed all these light management techniques, we discussed the concepts of the Lambertian scattering, étendue, and plasmonics. Finally, we looked at the 4n square Jablonowicz limit, which describes how much absorption in a semiconductor slab can be enhanced through light management. In the final week of PV1X, we discussed the Shockley-Queisser efficiency limit for solar cells. The Shockley-Queisser limit describes the maximal theoretical efficiency of semiconductor as a function of its bandgap energy. This limit only includes the fundamental losses due to spectral mismatch, radiative losses and band gap utilization. The Shockley-Queisel limit makes a number of assumptions that are challenged in third-generation PV concepts that aim to overcome the Shockley-Queisel limit. These assumptions are that a photovoltaic device only has a single junction with one band gap energy. The device is illuminated by one sun. That photons with an energy below the band gap are not used. That only a single electron-hole pair is generated for each absorbed photon. And finally, that the excess energy of high-energy photons is lost due to thermalization. The third-generation concepts that challenge these are multi-junction solar cells, concentrator photovoltaics, intermediate band solar cells, spectral up and spectral down conversion, multi-exciton generation, and finally hot carrier solar cells. Now you understand all the optical losses in solar cells and what is being done to minimize those losses. The mitigation of these losses can be translated into 3 solar cell design rules, namely spectral utilization, light management, and band gap utilization. Designing any type of solar cell involves a delicate interplay between these 3 pillars. That concludes this PV1X summary. I'd like to remind you that if some of the topics seem unfamiliar, we encourage you to return to the PV1X course and revisit those topics. I wish you good luck with the upcoming exams.